We need to know the stages of the nuclear power station. First stage. In a nuclear reactor, the nuclear fission, which produces the heat, is able to heat the water and make it boil. So the nuclear energy turns into heat energy and makes the water turn into steam. Then the steam is forced through the turbine and it makes the turbine turn round. The turbine is connected to the generator and the generator is able to produce electricity. Some steam has to be taken away and cooled down in the condenser, and then this water is reused as it's reboiled to produce the steam here. You need to know the role of the heat exchanger in a fission reactor. Okay, here we have the nuclear fuel. It heats up the liquid here to super high temperatures. So all of this is very hot indeed. Then we have what's called a heat exchanger. An external source of fluid is pumped through these pipes. As it goes through, it heats up, takes the energy away from the reactor, and then it's taken away, and then that is turned into steam, and we're able to produce steam to drive a turbine. And here we have the same thing here. Now, the control rods, what are they? These basically control the reaction by absorbing neutrons to prevent further fission. Remember, a nuclear bomb does not have control rods. The nuclear reaction does not need to be controlled. But this chain reaction is controlled, so it doesn't get out of control. Then we have what are called moderators. The moderators slow down the neutrons so that absorption of the uranium-235 can occur. When it absorbs the neutrons, it goes from uranium-235 to uranium-236. If the neutrons are not slowed down, in other words, they keep the high speed, they will not be absorbed by the uranium-235, they will be absorbed by the uranium-238 instead. U-238 does not go to a fissionable isotope, and therefore they cannot take part in the nuclear fission. So the moderator. So this is made of graphite or water, and they slow down the neutrons to a speed at which they will be absorbed by the nucleus, by the uranium-235 nucleus, and then it becomes uranium-236, and then it will fission due to its instability. Fast-moving neutrons, however, do not cause further fission. They will be absorbed by 238, which then does not fission. Control rods. These, for example, are these rods made of boron, and they absorb the neutrons. They don't slow them down, they completely absorb them, and they make them not available for further fission. And they basically slow down the rate of the nuclear reaction, not the speed of the neutrons, but the rate of reaction. So energy is released in a slow and a controlled way. Now you need to know about neutron capture by the uranium-238 in the production of plutonium. So first of all, you can write the nuclear equations for these. Uranium-238 absorbs a fast-moving neutron, so it becomes uranium-239. Neutron plus 238 goes to uranium-239. Then the uranium-239 spontaneously decays, not fissions, but decays to neptunium-239 with a beta particle and an antineutrino. So you can draw that now. You can draw the nuclear equation for that. Don't forget the antineutrino. Then this neptunium-239 will decay to plutonium with the same process, producing an antineutrino and a beta particle. So we have plutonium now, plutonium-239 is fissionable, so the plutonium can be used as a nuclear weapon. So remember that 238, which is not very useful in a nuclear power station because it doesn't fission, can be used to make plutonium, which is fissionable, which can be used as a weapon. Now, to sum up the difference of the uranium-235 and 238. Remember, 235 is a very rare isotope. It has to be enriched to make it greater than 3%. So we have 235, which is fissionable. Basically what we have to do is that we have to fire a slow-moving neutron at the 235. It becomes 236. Then suddenly split. The 236 is not stable and it will fission. So we get these fission products, the two nuclei that are produced, plus high energy neutrons. And this is the energy that's released in a power station or in a nuclear bomb. On the other hand, 238, which is a majority of uranium, is non-fissionable. And this absorbs the fast-moving neutrons, so it will become another isotope. So it becomes uranium-239. But then uranium-239 decays to neptunium-239 via beta decay, and then neptunium-239 will decay to plutonium-239. Plutonium-239 is fissionable. It can be used as a nuclear fuel and can be used as a nuclear weapon. Describe the importance of plutonium-239 as a nuclear fuel. Plutonium can be used as a nuclear fuel in another reactor. The reactor has to be designed differently, or it can be used in nuclear weapons. You know about the safety issues and the risks associated with the production of nuclear power. So first of all, thermal meltdown. What is this? Now, you need to be able to produce enough heat to produce the steam, but also the reactor is kept cool by using coolants. Now, if it heats up too much, the moderator might melt, and so the cooling system has to be kept working. If it doesn't keep on working, then the nuclear reactor will melt. It doesn't explode like a nuclear bomb. It just will start to melt. And here is the famous remnants of Chernobyl. This is the nuclear reactor, which was basically destroyed because of thermal meltdown. So the whole nuclear power station was destroyed. Another issue is nuclear waste. Now, after you have used up the uranium, you're left with products that have very long half-life. So we need to dispose of this waste. We can bury it underground, but what happens if there are leaks? Also, with uranium-239, you know that it can be recovered and you can use it to make plutonium, which can be used as weapons. So it's not a case of actually just getting rid of the uranium-239, because that can be used by agencies, political bodies or whatever, to make nuclear bombs. This is an example of the disposal of nuclear waste by digging a deep hole in the ground and leaving it there for thousands of years. With volcanic activity, there could always be disruptions and disturbances which could expose this material. And the last one is the mining of uranium. Uranium is mined there has to be mined in closed mines because it produces radon gas, which is radioactive, and therefore it has to be closed, and the waste that is produced by the mining of uranium is also radioactive. And here we have a sketch. You notice that the mine is not open. It has to be sealed at the top, and it has to be controlled so this gas is absorbed and is taken away. You need to know about nuclear fusion. Now, the problem with nuclear fusion is that these particles, before they join, have to be moving so quickly. They have to be in a temperature and a pressure which is very high. So they need to be moving fast enough to overcome the electrostatic repulsion between these positive particles. And they must be at such a high temperature that they can't even touch the walls of the container that they're in, because then it will cool them down too much, and this plasma, this ionized substance, will react with the walls. So it has to be kept in basically a magnetic chamber called a tacoma, which is like a donut shape. Here we have hydrogen 3 and hydrogen 2, which is tritium and deuterium. They fuse and produce lots of energy and makes helium and neutron. This is a process that basically happens in the sun. You know that energy is being produced because if you look at the mass of the tritium and the deuterium and the mass afterwards, there's been some mass that has been lost. There's a mass defect, and that will produce energy either in the form of radiation here or the speed of these particles, the kinetic energy of these particles. And here we have an example. Deuterium and tritium come together. They fuse and they make an alpha particle and a neutron. Where does nuclear fusion happen in nature? The only place we know it happens is in the production of helium, which is in stars.